the first of our series of review videos. So as we have worked through this content, we've been organizing our material into units. And if you go on College Board's website, you can see that they have categorized all of their content into 9 units. And that's what we're working through with the personal progress checks and the practice problems. That allows us to look in depth into each unit and see what concepts you're really good at and you've really mastered, and which ones you need to go back and review. However, College Board also organizes their content and their questions into what they have called their 6 big ideas. And this is sort of a broader approach. It's the main 6 topics, ideas, concepts that they think are really important for a fundamental understanding of chemistry. And so for our review videos, we're going to go through those 6 big ideas. Now the first one is called Atoms, Elements, and the Building Blocks of Matter. And the main point of this idea is being able to understand and explain the role that atomic structure has on material properties. So here is sort of an outline of the concepts that fit under this big idea. We can look at the periodic table to be able to describe the trends and the arrangement of that table based on the structure of the atoms. We need to be able to use atomic mass and moles in calculation problems. We need to be able to talk about electron configurations and how that influences a material's property. We'll talk about Coulomb's law, as well as a couple analytical techniques that you might see come up as well. And then we're actually going to start with just a quick overview of some of the really famous scientists and really famous experiments that helped us develop our current understanding of the atom and atomic structure. So we'll start here, then we'll talk about some of the analysis techniques and finish up with the rest of these ideas. So most of this, again, should be review. We're not going to go really in depth to any of these concepts because for the most part we've already talked about them. So if you want more detail, if you want to go more in depth, I'd say either find a video specific to those concepts or go back and look at our earlier slides to review those in more detail. But most of the stuff should sound pretty familiar to you. So we're going to start with a couple of the really famous experiments, just in case you end up needing some of this background information. So the first was called the cathode ray or cathode tube experiment. This is what clued us into the existence of the electron in the first place. Scientists discovered that streams of negatively charged particles emanated from cathode tubes. So J.J. Thomson set up this experiment to prove the existence of the electron and also to measure a charge to mass ratio of the electron. So that was really useful. And once we had that charge to mass ratio, another scientist came along and realized that if we could measure either charge or mass, we could use that ratio to calculate the other. So the next famous experiment was Millikan's oil drop experiment, performed by Robert Millikan. And this experiment allowed him to determine the charge on the electron. So what he did was essentially he's got an atomizer here spraying in oil droplets that fall through this very small tube in this plate. And once they are between these two plates, they get ionized. So they become negatively charged. They pick up electrons. And then he's able to tune the electric field between these two plates, make it this plate more positive or this plate more negative, and see how that affects the speed at which that ionized drop falls. Because of course, a negatively charged particle would be attracted to the positive plate, repelled by the negative plate, but would also feel a downward force by gravity. So at some point, those had to cancel out. The force of the electric field trying to repel and push the oil drop up, and the force of gravity trying to pull it down. And from that relationship, he was essentially able to calculate the charge of the electron. And once he knew that, he also knew the mass. So that got us a long way. We knew that electrons existed. We knew about their size and mass. The only thing that was left is that we didn't really know where they were. And so that brought us to probably the most famous of this set of experiments, Rutherford's gold foil experiment. Remember, before this experiment, it was thought the model for the atom was the plum pudding model, right, where there were electrons floating around in this positively charged jelly. That the positive charge was distributed everywhere in the atom, and there were a couple of electrons floating around. So when Rutherford performed this experiment, he shot alpha particles at this sheet of foil, and he was expecting that they would exclusively go pretty much straight through, because they shouldn't have been hitting anything. They should have been able to go through that positive jelly. We knew electrons were tiny. They shouldn't have interfered with the alpha particles. And so he was expecting to see all of his results right here on the detector. And remember, he then had a grad student go back and check other angles pretty much just for the heck of it, and they were very surprised to see results show up with these wide scattered angles. This is what made them go reevaluate and redo their atomic model. They said for the alpha particle to be deflected at such a large angle, it must have hit something pretty big. It must have hit something really dense and really positive. And so that's why they made the nuclear atom, the new atomic model, where there was a nucleus in the center of the atom, where all the positive charge was stored, and then most of the atom was empty space. There's electrons around here, somewhere in this cloud, but it is largely empty space. And so understanding that can really be a big part of explaining some of the trends, some of the material properties and atomic structure properties that you might be asked about. All right, so that's the main idea. The atom is mostly empty space. All right, let's talk about a couple analytical techniques that sometimes come up in questions. You might be given a description of an experiment and a set of results and asked questions about that. Now, the good thing about this, is that if you're given a data table or a chart or a graph, that gives you all the information you're going to need, most likely. If you're able to look at the x and y axis, figure out what the graph is telling you, you can probably figure out the question without even needing to have any idea of what the experiment behind it entailed. And you'll see in a second, this might start looking familiar. I threw a couple of these at you on previous take-home tests to try and get that skill developed as well. But for the sake of having thorough background information, let's talk about it a little bit. So a common technique that comes up is mass spectrometry. Mass spectrometry. And this is going to separate compounds or atoms by mass. Any spectrometry experiment is some sort of separation, and in this case it's by mass. And so you will largely see this when we are trying to determine the mass and number of isotopes for an element, and I'll show you why in a second. You can apply it for other questions and applications as well. You could use it to get a whole molecular structure, but most often it seems if it's going to come up on an AP test, it's going to be for this application. Let me just quickly walk you through what happens in a mass spec. So let's say we're looking for isotopes. So we've got just one type of atom. We're wondering how many isotopes it has and what is the mass of those isotopes. So in here we would have our sample, our gas, and it gets ionized very, very early right here, and because it's ionized it has a negative charge. Alright, now there's a negatively charged plate here to repel those negatively charged pieces away. And there are positively charged plates here, and as they pass through, they get faster and faster and faster, right? There's a whole bunch of positively charged things trying to pull them through, and so they speed up, they're accelerated through here, and they pass through a curve here where there's a magnet on both sides. Now, the lighter isotopes will have a large effect from these magnets, right? It's pretty easy to kick something light, to move something light, to deflect something light. And so the lighter ones get deflected and they don't reach the detector. And the heavier ones have a lot of momentum. It's hard to change their course. And so they carry through and they don't reach the detector. But whatever our mass spec was tuned to, that exact mass is deflected just enough to perfectly reach our detector. And so the cool thing is that we can change this magnet strength. We can change how much it should be deflecting. So here, as you can see, we've captured the neon 21. But we would continue to tune this and change this magnet and the deflection angle here so that we could capture neon 20 and neon 22 as well. We'd change how strong the magnet is so that sometimes what it's tuned to, as we go through the series of tunings of deflections, we capture the neon 20 at one time, we make the magnet a little stronger, now we're capturing neon 21, and we make the magnet a little stronger and we'd capture neon 22 on the detector. The two lighter ones would have been deflected away from it. That's essentially what's happening. We're just bending ions through here depending on their mass and charge ratio. Now luckily, since we care about isotopes, all these have the same charge, so the only thing that's changing their deflection angle is the mass. And we'll get results that look like this. So this may look slightly familiar to you. I'm going to go to the next slide where there's a bigger picture of one. We had this on a take-home test first semester, I believe. And so the cool thing, like I said, if you didn't know how a mass spectrometer worked, you could probably still answer any relevant question given this data table. If you just look at the x and y axis, let's see, we're given mass and we're given relative abundance. So even not knowing that this came from a mass spectrometer, we could answer that there are 2 isotopes shown for boron, 2 isotopes shown for chlorine. We've got the approximate mass of each. We've got its relative abundance. We could do lots of things with this. We could calculate the average mass. We could predict that the average mass is closer to boron 11 because it's much more abundant. But it is helpful to have the background information to know where that came from. These are fairly popular question types. There was one on the Unit 1 progress check that we did. So go back and look at that question again now and look at your answer, look at the scoring guidelines for the correct answer, and compare it to what you know now. Oh, one other important note. Remember that when we're calculating the average mass, we take the relative abundance times the mass. So the relative abundance, written as a decimal, not a percent, times the mass of this first isotope plus the relative abundance as a decimal times the mass of this second isotope, and then we just add them together. We wouldn't have to divide by 2 here because we've already accounted for the abundance. We've already used a decimal place to make it a more reliable number. It's a weighted average now, instead of just adding the two masses and dividing by 2, which would have gotten us 10.5 exactly. We know the average mass is going to be higher than that. It's going to be closer to 11 than it is to the middle, or to 10, because there's much more of this. So there's no need for division in that formula. Alright. Again, here's just another format, another way that type of graph could appear. It's telling us the same thing now. We've got here 1, 2, 3 isotopes of silicon, their relative abundance specified above them, and their masses. And so we could use this set of numbers here to calculate the average mass of silicon. Go ahead and try that. Make sure you can properly apply that formula. You should get about 28. And of course, we see that this is reasonable. There's much more of the silica 28 isotope. Our mass should be pretty close to it. There's a bit of the higher mass isotopes, but they are so low in abundance that they're not able to bring up the average mass that much. One other one, this one does not appear as often, but it's worth bringing up just very quick. One other analytical technique you might see is called photoelectron spectroscopy. What we're doing here is we're trying to figure out where the electrons are in a material, or how tightly they are bound. And so we've got our sample here, and we're just going to shoot a bunch of X-rays at it. And we can tune the energy of these X-rays, so we can tune their strength to keep shooting stronger and stronger X-rays at this material and detect the electrons that those X-rays knock out of the material. Notice there's an argon gun over here. That's just for safety purposes. Argon's an inert gas, remember. We'd rather have that in here than oxygen when we're throwing really high energy stuff at metal and making it eject electrons. We'd rather this whole thing not start combusting, so there's an inert gas to make sure there's no oxygen. So these results might look something like this. And again, this could be really confusing if you just got this data chart and you had never seen it before. Again, we saw one of these on a previous take-home test. It was formatted slightly differently. We just had one axis with higher energies over here and lower energies over here. This one has been stacked in 3 just because of the scale length. So we've got 0 to 10 on the bottom, 10 to 100 in the middle, and 100 to 500 on top, telling us the energy of the X-ray that was used. And then we've got these peaks, which say give us our relative number of electrons. And so let's figure out how we can use this. Alright, so we've got 3 peaks of equal height and 1 peak that's a lot taller than the rest. Now, since this is relative number of electrons, these 3 peaks of equal height must have the same number of electrons. Alright, let's look at our highest energy first. So we know that these are electrons, and if we know that we're using photoelectron spectroscopy, we know they're electrons that have been emitted from a sample as a result of this high energy X-ray hitting them. So, in terms of orbitals, in terms of valence shells of electron locations, think to yourself, where are these highest energy ones going to be located? And you should be able to come to the conclusion that the highest energy ones are going to be the ones closest to the nucleus. So these are going to be our first shell, our 1s shell. And we know that the 1s shell holds 2 electrons, so we're able to say for sure that this peak height corresponds to 2 electrons, which means we can fill in the 2's for these peak heights that were equal as well. This peak height is 3 times as tall, so it's going to be 6. 3 times 2. So now we know how many electrons each peak corresponds to. And as we go from 100 to 10 to 5 to maybe 1 or 2 on our energy scale, as we go down in energy, we're getting farther away from the nucleus, right? It takes less energy to cause this electron to be ejected because it's all the way on the outside. So we could use this to write our electron configuration for an atom and to identify it. This high energy one, wherever it is, the highest energy peak is going to be the 1s orbital. So we've got 1s2. All right, next up is 2s2, 2p6, 3s2. And once we've got that configuration, we can look at our periodic table and identify the element as magnesium, because that's where the 3s2 element is. One thing we talked about fairly briefly was Coulomb's law. We don't often need it in its equation form to actually plug in numbers and solve. It's come up occasionally. I think it's a given equation, but normally it's more important on the concept side. It's more important to know that the amount of energy that an electron has depends on its distance from the nucleus. Remember, the farther out an electron gets, the less attraction it has to the nucleus. The less tightly the nucleus is able to hold it, and the easier it'll be to remove. And that's governed by Coulomb's law, which has a constant, the charge of both the nucleus and the electron, divided by the distance squared. So as we get farther and farther away, the force that the nucleus is applying to the electron gets weaker by a squared factor. It gets a lot weaker. Quick reminder about conversion factors. We have the concept of moles, which we know is just another unit, and that helps us convert between grams and formula units. If we go down here, it's our bridge from the molecular scale to an actual measurable scale. We can't measure a total number of molecules or formula units, but we can measure a total amount of grams. So just a reminder, if nothing else, master your conversion factors. It's probably one of the most important skills, both as a chemist and as a aspiring chemist taking the AP test. Be able to keep track of your units. It's not just for conversions, but for any problem really. Keeping track of units using dimensional analysis is very, very helpful. It will automatically let you know if you've set your problem up right, done your math right, because you should always be able to find the units working out to what you expect. So use the railroad tracks if that makes more sense to you, or set them up by multiplication, but definitely make sure you're comfortable doing conversion problems. A lot of the problems on the test could be done like a conversion problem. One thing you might remember talking about is combustion analysis. These were fairly long problems. Essentially, we put in a known mass of a sample that contained carbon, hydrogen, and sometimes some oxygen, and we burn it. We let it combust. And then on the outside, we've got a material that will absorb H2O and a material that will absorb CO2. Of course, we know that combustion will always involve the addition of oxygen. We'll have to have some oxygen in this chamber for it to burn, because oxygen is required for combustion. And we know that when a hydrocarbon burns, the products will always be carbon dioxide and water. These should be our two products if we have cleanly combusted this material. And so we go out here, we find the mass of CO2 we absorbed. From that, we find the moles of CO2 we absorbed. which could then tell us the moles of carbon we absorbed and the grams of carbon we absorbed. Same thing for H2O. We know the mass of H2O we absorbed, so we know the moles of H2O, so we know the moles of hydrogen and the mass of hydrogen. Now, if there was originally oxygen in our sample, then we'd have the mass of hydrogen that came out, the mass of carbon that came out. The sample is the only source for those masses. If we subtract those masses away, we'd be left with the mass of oxygen that had to be in our sample originally. Finally, once we know the mass of oxygen, carbon, and hydrogen that originated in our sample, we can know the moles of carbon, hydrogen, and oxygen that originated in our sample. And remember, way from the beginning of the year, this is where we had that sort of big chart that took up the board, and we divided each line by the smallest number of moles, and that got us the numbers, the relationships, the subscript that went with each element in our compound. Might be worth going back and reviewing a combustion analysis problem to make sure you're comfortable performing those as well. You might not think that electromagnetic radiation fits in with the atomic structure idea, but they're actually very interconnected. So if you recall our discussion on light, photons, and electromagnetic radiation, some of the main ideas were that all of this radiation travels at the same speed, the speed of light, 3 times 10 to the 8th meters per second. And our visible light is the region from 400 to 750 nanometers. We've got variation here in wavelength and frequency. And remember the relationship. The longer the wavelength is, the shorter, the smaller the frequency. So the longer the wavelength is, the more we've stretched out the wave, the less copies of that wave we're able to pass by a point at a certain time. The shorter our wavelength, the higher our frequency. If our waves are really close together, we can pass a lot of them through a point in 1 second or one given unit of time. The reason this is connected is because the knowledge of photons and light and energy can also be used to identify elements. Each element has a unique line spectrum. Remember when we talked about the emissions of different elements? This is what we did the flame test for, to see what color light different elements emitted, and we could identify elements based on that color because they were all unique, and it had to do with where their electrons were, how far, how many shells, how big of an energy gap the electrons crossed, influenced how much energy they released as a photon. And as we know, the energy of a photon is related to its wavelength or its frequency. And since it controls the wavelength, it controls the color. The fact that we've got these really distinct lines with just nothing, just black in between, indicates that electrons can only make certain jumps. They've got certain allowed energy levels where an electron can be here at this energy or here at this energy. There's no line, there's no color in between, because the electron's not allowed to have any of those energy values. Remember our model of the atom where we started adding shells and energy levels and rings because the electron could only be at certain places. Here's just sort of another way of expressing that. Since the gaps between states get closer and closer as our principal quantum number increases, as we get farther away from the nucleus, the frequency of the light that is emitted changes. So if we're going from n equals 1 to n equals 2, that was a very large energy gap that needed to be overcome. And so we'd have to input that energy to allow the electron to make that jump. If it then falls back down, it needs to emit that exact same amount of energy because it is only allowed to have a very specific energy value to be in either of these shells. Now, if we make a farther jump, if we go from n equals 3 to n equals 1, we have a larger energy gap. We have a photon that's released with even more energy. More energy means a higher frequency, a shorter wavelength. And then that's the demonstration here as well. If we have a smaller energy gap, only going from n equals 3 to n equals 2, less energy is released. So we've got a longer wavelength and a smaller frequency. Some key terms when we're talking about this: the ground state energy level is the lowest energy level, the n equals 1 energy level, the first ring next to the nucleus. An excited state is anything above that, so any higher energy level above the first 1s orbital. Absorption is when an electron moves from a lower energy to a higher energy level. It absorbs energy, it moves up to a higher energy orbital. And emission, if an electron then falls back down, it moves from a higher energy level to a lower. It has to release, it has to emit whatever extra energy it had as a photon. Here's a quick look at our quantum numbers chart. You should have this in your notes, so we put it up on the board and copied it into notebooks. Try and refamiliarize yourself with what each of these quantum numbers meant and what values were allowed. And a reminder of the shortcut using the periodic table to write an electron configuration. Remember, it's organized so that our row number gives us our principal quantum number, the d orbitals being an exception, and then we just move across the rows. We've got the s block, the d block, and the p block, so as we move through we can fill out our electron configuration. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 3, 4, 5, 6, 3s1, 3s2, and so on. Remember the couple of special rules when we start to hit the d block. These are offset by 1, so in row 4 we've got 4s and then 3d. Remember that the d orbitals were really complex, really spread out, and so they are actually higher in energy than the preceding s orbital. The f blocks are offset by 2. Remember that these belong in this region right here. So it would go 6s, 4f, 5d, 6p, 7s, 5p, 6d. There were 3 rules that governed how we filled orbitals. The Aufbau principle said we fill lower energy orbitals first. Hund's rule said orbitals of the same energy are filled with electrons until all are half full before pairing up electrons. So this was if we had 3 rooms, for example, in the p orbitals, we would put 1 electron on each line, 1 in each room, before we'd force any to pair up. And the final rule, the Pauli exclusion principle, said that individual orbitals only hold 2 electrons and each should have a different spin. This is why we always had 1 up arrow and 1 down arrow if the electrons were going to share the same line. Also remember the maximum allowed electrons in each orbital. S orbitals can hold 2, p orbitals 6, d orbitals 10. This is really easy to remember if you're using the periodic table shortcut. The s block only has 2 columns in it. We can only ever get to s2. The p block only has 6 columns in it. We can only ever get to p6. One other thing that you can determine if you have drawn out the electron, the orbital diagrams with the lines and the arrows, is the magnetism of your substance. So recall that diamagnetic substances are not attracted to magnetic fields. And this would be a case where there's no unpaired electrons. There's nothing unpaired, there's nothing to be attracted to the field. Paramagnetic substances are ones that are attracted to a magnetic field. These are substances that do have unpaired electrons. So maybe an atom that had a 2p3 in its electron configuration. It would have 3 unpaired electrons. 3 singly filled orbitals, each has 1 electron in it, 1 arrow pointing up. All those are unpaired. There's nothing to balance out their upwards spin, and so they are attracted to a magnetic field. One special case is ferromagnetism. This is when the spin of the unpaired electrons in a solid happen to align themselves all in one common direction. That's just a special case of paramagnetic. I imagine that these two key terms come up much more often than this one. If we were going to measure this effect, we could set up an apparatus like this. We've got an electromagnet here. It's currently off, but it's ready to be turned on. It'll provide us a magnetic field when it is on, and we have balanced up here our sample with a mass. Now, if we turn the electromagnetic field on, if the substance is paramagnetic, it will be attracted to that field, it will be pulled down, and so we can measure the force of that attraction because it will pull our scale and the mass down. The paramagnetic effect is going to be proportional to the number of unpaired electrons. So if you've got 2 substances you're comparing and one has 1 unpaired electron and one has 3 unpaired electrons, the one with 3 is going to have a more paramagnetic effect. Alright, I'd say probably the most important concept from this first big idea is being able to explain periodic trends. This is a very common topic that you could be asked about, and so periodic trends can include atomic size, ionic size, ionization energy, electron affinity, nuclear charge, but they're all going to come down to what's going on with the electrons. How tightly are the electrons held? And so if we just think about size first, think about moving down a column. What's happening? Well, as we move down a column, our principal quantum number is increasing by 1. That means we're adding an energy level to our atom. We're adding a whole nother shell of orbitals. And so, of course, our atomic size is getting bigger. We're moving out to a higher and higher energy level. As we move across a row, our atomic size gets smaller because we've got the same energy level, the same shell, but as we move across, we add 1 proton to the nucleus each time we move across. And those extra protons allow the atom to pull the electrons in closer, hold them closer together and more tightly, so the atom gets smaller. The rest of the trends can be understood from that same idea as well. Ionization energy is the amount of energy required to remove an electron. So the farther out an electron is, the less tightly it is held, the easier it's going to be to remove, and the lower its ionization energy. Also remember that we can remove more than 1 electron. The first ionization energy is the energy needed to remove the first electron, and then the second ionization energy to remove a second electron after that. Typically, it's easier to remove the first one. We'll look at these trends. So typically, as we go across a row, it gets harder to remove an electron. Let's look at this row that starts with lithium and ends with neon. It's getting harder and harder. We're needing more and more energy to remove the first electron as we go across this row. Because of course the atom is getting smaller, there's more protons in the nucleus, there's a larger effective charge from the nucleus is better able to hold on to its electrons, to hold them in close and tight, and it's hard for you to remove them. Ion size is similar. It's also going to depend on the number of electrons and the nuclear charge, though. So here we've got elements forming cations. So they are losing electrons. So they're going to get much smaller because they're losing electrons. Now the protons in the center can do a better job of pulling the remaining electrons in close because they don't have to divide their charge between an additional electron. There's one less charge to take up their energy. And so the ions get smaller. For the anions, our anions get larger because we're adding electrons. We're making it harder for the protons in the nucleus to hold on to all of these electrons. Now they're having to spend some of their energy on an extra electron, and so they're not able to hold everything in as closely. In an isoelectronic series, we'd have ions with the same number of electrons. In this case, our ionic size is going to decrease with an increasing nuclear charge. Of course, in this case where we've got the same number of electrons overall, the greater our nuclear charges, the more protons we have, the smaller that size is going to be because those protons will be able to hold on to the electrons better. Here's a summary of the periodic trends. This is really helpful. It can help you predict. It can help you compare two or more elements of what's going to be larger, smaller, have a greater or lesser ionization energy. But memorizing these trends is not the same as explaining them. You can know the trends and use them to make predictions, but if you're asked to explain why something is bigger or smaller, you'll have to go back and talk about what's happening with the electrons, what's happening within the atom, within its structure, to control its size. All right, molarity also fits into this section. This was a way to talk about the concentration of either ions or atoms in a solution or in a volume. Typically, it's used to measure the concentration of solutions. And this, the formula for this was moles of solute over volume of solution in liters. This is the most popular way to measure concentration, but it is not the only. I would be very comfortable using molarity and using this formula, but do keep in mind the other ways to express concentration. There is also molality, there was mole fraction, there was percent by mass, and percent by volume. So just make sure you're able to keep those straight and know and apply the formulas. If we are trying to create a solution with a specific concentration or molarity, there's a very standard way to do this to make sure you're precise. And so if you are asked to describe a process or an experiment, this might be one topic that comes out. So remember, anytime where you are asked to dissolve an anytime you're asked to design or describe an experiment, there are a couple of things you can make sure you always include. Always make sure that you specify what you're going to measure. Are you measuring mass or volume? And how are you going to do it? If you're measuring mass, you're using a balance. If you're measuring volume, you're using a graduated cylinder. And you should also always throw in what you're going to do to reduce your experimental error. Are you going to do this experiment 3 times, 5 times, things like that. So if we're preparing a solution, we'd weigh out our solute. So if we were going to dissolve salt in water at a specific concentration, we'd calculate how many moles and then how many grams of salt we needed, weigh it out on a balance, and transfer it to a volumetric flask. We always prepare solutions or dilutions in volumetric flasks because it is easiest to keep the measurements here very precise. We would dissolve the solute in a small volume of solvent, not enough to fill the flask, just enough to cover and dissolve the solute so that we can swirl it down here. Once it was dissolved, we fill the flask to the marked line on it, guaranteeing that we have a very specific total volume. Here's just one more way of showing that. We always dissolve our solute first before we have filled up the flask, then we fill it to a known volume. This guarantees that we've got a certain number of moles of solute because we measured them and dissolved them, and a very specific total volume of solution because we filled to that line after dissolving. If we've prepared multiple solutions, we could also dilute them from there. That uses the dilution equation, M1V1 equals M2V2. If we know our starting solution and starting volume, and we know how much we're diluting it to, we can figure out its new concentration. One more reminder about spectroscopy and other analytic techniques. This one we didn't spend a whole lot of time talking about, but it is fairly intuitive. Another spectroscopy method is called UV-Vis spectroscopy. It's based on the absorbance or transmittance of light through a material. And so as we know, almost every material will absorb some wavelengths of light. And we can measure what wavelengths are being absorbed and how much of them are being absorbed using a spectrophotometer. And this information helps us understand the composition and concentration of our sample. Now, this sounds really confusing, but really what it boils down to is we've got a sample, we're going to shine light through it, and basically we're going to detect what wavelengths made it through the sample. And that would be graphed for us in an output. The important thing about spectroscopy is remembering Beer's law. Typically, you won't be given spectroscopy data. You won't be doing calculations. Typically, this is a concept-based question as well. And again, this is fairly intuitive. The law says that the absorbance equals ABC, the molar absorptivity. Sometimes this is given by this Greek symbol instead of A, but it means the same thing. This is a material property. It's how absorbent the material is. Times its path length. Hey, the thicker you make a material, the more light it's going to absorb. Times the concentration of the sample. Think about looking at 2 cups of blue food coloring. If you've got two tall glasses of equal size, and one is half full and one is all the way full with blue food coloring, and you're looking at it from the top, you're looking down at it. The one that's all the way full, it's going to look darker. It's got a higher path length. Now, dump those out, put blue food coloring in both, or water with blue food coloring in both, fill them to the same level, and then add a bunch more food coloring to the second. That one's going to look darker. It has a higher concentration. So you might get questions on there asking about these factors that change the absorbance. But you can, this law is given on your equation sheet, so you can use that to reason through an answer. Here's an example of this sort of spectroscopy. So it's a calibration curve, meaning we did 3 samples in here of all the same material, but we increased their concentration and measured how their absorbance changed. And as expected, as we increase their concentration, the absorbance also increases linearly. All right, that was our first big idea. Let me know if you have any questions over these topics.